let us start. And the objective for today is kind of to talk about what we were discussing last time, which was multi-layer perceptron or fully feed-forward neural network, I mean whatever you call it. We started talking about a neural unit, and the last lecture we ended by showing you a smaller neural network. So, we will continue on our discussion from there, and then we will go into training algorithm towards the end of today's lecture, right. So, that is kind of the idea. So, with that background, let me start. So, this is lecture 4. Okay. So, for a quick recap, last lecture we talked about a single neuron unit, right. So, we talked about a single neuron, and can you remind me what was the equation for the single neuron? There, y is equal to sigma or f, right. So, the equation was for a single neuron, keep that in mind, right. Y is equal to sigma W transpose X plus B, okay. And this W we call it our weight, B we call it our bias, W and B together we will call it as our parameters, and this sigma we call it as our activation function. From where the name activation function comes into picture? Why is it called activation function? Biological, activating or not activating, passing information, not passing information, 1 or 0, fundamentally the perceptron, the threshold function. That was the original idea, and that is why we started calling it activation function. But for practical purpose, what is sigma? A nonlinear function. For practical purpose, it is just a nonlinear function, that is all it is, right. So, for practical purpose, this is my nonlinear function, okay. And this is not nothing new. This is something we have already discussed in our last lecture. And if you remember, the last lecture we ended with the statement that a single neuron might not have enough expressive capability. And so, the idea is that just like in human brain, it is not a single neuron. Our artificial neural network should not have a single neuron, it should be a network of neurons, and that will have hopefully adequate expressive capability, right. So, in neural network, we have multiple neurons connected in form of a network, connected as a network, right. This is what we have, and the last lecture the same diagram I am going to draw. So, if you remember, the diagram was something like x1, x2, xk, and then you have your h1, h2, hp, and then y, okay. And then I circle it, and then I connect it. Okay. So, this is more or less my neural network. Each of these circles you are seeing, those are my neuron mode, one single neuron, each of the circles, and then each of the arrows you are seeing, those are showing me the network. So, this neuron should be connected. So, those are showing me the connection. Now, although I did not specify, you can keep it in mind that each of the edge will be associated with a weight, and each of the neuron except the first layer will have a bias of its own, will have a bias of its own. Okay. So, each of these each of the edges will have a weight. So, number of weights is equal to the number of edges. Each of the nodes except the x will have its own bias, and so you can calculate the number of parameters in a network given that you know what is p, what is k, and both of these, right? And yeah, so that's it, right? And remember, I mean, the one more thing we did was we wrote down the equation. So, let me write down the equation once more. So, the equation is, if I have to write H1, this is equal to, let us say, sigma 1 W maybe 1 I will say, W 1 transpose x plus b. Why am I using 1 because H2 I will probably write 1 2. When I write HP I will write 1p.
Why does sigma has an index?
Correct, because there might be a sigma going from H to Y also,
Varying sigma.
that it is generally varying. Okay. Within a layer it need not vary. I mean, most of the cases we do not vary within a layer. But when you go from one layer to another layer, like from X to H and H to Y, they can have their own sigmas. In fact, often they do have their own sigmas. For example, if you are solving a regression problem, generally the last layer is a linear layer, no sigma. If you are solving a binary classification problem, the last layer is sigmoid. If you are solving a multi-class classification, then softmax. So, the last layer is decided based on the problem you are solving. The previous layers are your choice, your convenience, your design, and all of those things, right? How well you can design these things. So, H1, similarly you can write H2 sigma 1 W12 transpose x plus b, and like that you can write the other H's, right? And then you have your y also. Y I will write it as sigma 2 W2 transpose H plus, okay, here I did not write, so I should write B2. Okay, and this one should actually be B11, B12, and something like that. Okay.
Why W11?
W11, good question. W11 is a vector. It is denoting that from x, I am calling this whole first layer x1, x2, xk as 1. So, W11 is denoting the connection between this first x1 to xk to h1. What is W12 denoting? Connection between this whole x1 to xk, that is my 1, to the second h2. So, to distinguish between those two, I am using this thing. Ultimately, in practice, you will not calculate like this. You will combine them, like write it in a vector form, and W11, 12 will become a W1, which will become a weight matrix. Right now, it is a vector. Yeah. So, this is what we wrote last time, and I said that sigma 2, you can imagine it to be a linear activation, which means no activation. And if you think of it like linear activation or no activation, then this h is my basis function. So, this can be thought of as a way that you are allowing the network to learn the basis function and then use those basis function to approximate the function. because because W11, W12, W1P, all of these things you are learning. B11, B12, B1P, all of these things you are learning. So if they changes, the basis function changes. So in some sense, you can imagine it like the network is learning the basis function, the linear combination of which will represent the output.
In last class, we wrote y is equal to A transpose H plus B.
Repeat once more.
In last class, we wrote y is equal to A transpose H plus B.
Yes. So because I was using the same notation. So A was, I mean, this W2 you can always write as A, right? I use the A because remember last lecture I also talked about linear regression. So to draw comparison with that, I used the term A. And because of the same reason, I did not use W11 and 12. I was using W1, W2. So that was to draw comparison with the linear regression we did in the same lecture. But now as I am going into the neural network with no reference to linear regression whatsoever, it will happen like that. So now I am trying to generalize and consolidate everything and write weights as W and bias as B. Clear?
W11 is the element of the weight.
No, it's a vector, one row or column.
That should not be Wi11.
Why it should?
All the
Yes, it's a vector, right? It's not an element, it's a vector. W12 is a vector. So it will have its first element, second element, third element, kth element. So W12 is a k dimensional vector. And x is a k dimensional vector. So you multiply 1 cross k and k cross 1, you get 1 cross 1. Add b, which is 1, you get 1 cross 1. So just to, because there are questions, I will just try to answer. So in this case, I am going to mark some of the arrows by green color, and those green colors are actually the W11. Okay. So can you, so this one you see, this one and this one, and then there are in between k minus 3 also. So this green arrows you are seeing, right? These are part of this W11 vector. Similarly, you can draw the other vectors in other colors and you can get it. Clear? If I write it in vector form, how will it look? So in vector notation, you will have, so now you see, yeah, this h to this thing I will write h. So you have h vector which is equal to sigma 1, and then W11, W12, this will come together. So I will call it 1 W1 x plus b. X is a vector, b is a vector, this thing. So this is when I write the first h1, h2 dot what hp together using the vector notation. So everything gets computed together. You will not do it one by one. That was written just for so that you can follow from before or to be consistent from before. But this is what actually you are doing. This is actually what we are doing. Very quickly, what is the dimension of H? P, right? So RP. What is the dimension of X? R K. Okay. What is the dimension of W1? It's a matrix. So R K H is what? P. So P cross K. If I write W1 transpose, I mean some books write W1 transpose, some books write W1. So depending on it will be P cross K or K cross P. So there, I mean both are used. I am writing W1. Why should I write one additional transpose? But yes. Okay. So this is P cross K. So it's a matrix, right? And you can now imagine that each of the column was W11, W12, W13, W1, P, something like that, right? Column or row, yeah. Sorry, each of the row was. right? Each of the row was W11, W12, W1 P. Okay. What is remaining? B. What is the dimension of B? B dimension should be same as the H dimension, because remember each of the neuron has its own bias. So number of neuron in the H should be equal to the dimension of the bias. So R P. Okay. Clear? Keep in mind I have written W1 and not W1 transpose. You can write either. Both are correct. The only change will be whether it will be P cross K or K cross P. Because at the end of the day you are learning this. You will be learning this thing, so it's will automatically get itself arranged. So should not be a problem. Okay. What?
W1 is P cross K.
Huh?
Then that is the W1 transpose.
Why?
Because P cross K
Times K cross 1. You get P cross 1. What are you looking at? What is W1 getting multiplied by? What is it getting multiplied by? X, right? What is the dimension of X? Okay. So, yeah. And there is a very nice theorem known as the universal approximation theorem, which shows, or which proves rather, that our neural network with a single hidden layer. Now remember, I have not even talked about what is hidden, what is layer. We will talk about that, but the UAT states that a neural network, which is a neural network with a single hidden layer, can approximate any continuous function, right? The proof of it I am not going to do, but if you are interested you can look into it on your own. So, there is this universal approximation theorem, and the statement is a neural network with a single hidden layer can approximate, or can represent, probably is the correct term, but anyways, any continuous function. Do you know of any other expansion that has a universal approximation theorem property? Taylor series, Fourier series. So there are others also, but these also have that property. Okay, so it's not new for you actually. I mean, Taylor series, I mean, all of you know about, and that can approximate any function, right? As long as it is differentiable, so continuous automatically comes there. Okay. I'll come to that. I have not defined it yet, right? So there are two things I have not defined, right? What does hidden means? What does layer mean? Okay. These are two terminologies I have not defined. Okay. In fact, there is one more catch here. But to go to that catch, let me go back and show you this thing, right? So layer here means each of the vertical nodes you are seeing together. So what is layer 1 here? X1, X2, dot dot dot, Xk. So each of the vertical line is one layer. So what is that is my first layer. What is my second layer? Correct. H1, H2, Hp. And the third layer is my Y. There is nothing but Y. Now out of that X1 to Xk, what are these things? Input feature. So this layer I will call my input layer. Y, what is my Y? So this layer I will call my output layer. Whatever is remaining after that is my hidden layer. Why the name hidden? Because you don't know the actual value of H. When you have this supervised learning setup, you have measured data, and data are in form of x comma y, I equal to 1 to n, right? You don't say x comma h comma y. So, H is actually hidden and flexible, and that is why you call them hidden layer. So, now this network is a neural network with one hidden layer, right. So, this actually is what this statement is saying. A neural network, this is a neural network with a single hidden layer. This has a single hidden layer, can approximate any continuous function. But you will see that this statement do not talk about what should be the dimension of P. How many hidden nodes should be there in that layer? Should P be 1, 2, 3, 10, 100, 1000, what? So, this assumes infinite. This assumes infinite. For practical purpose, you can imagine this assumes very large number of nodes, which you will never have. I mean, which is not a good idea, and that is why people do not use generally a neural network with a single hidden layer. Rather, what they do is you include multiple of these hidden layers, and the idea is, what is hidden layer doing, by the way? It is taking the input, doing some projection Wx plus b, adding a nonlinearity. So, it is doing some nonlinear projection, right, and that projection you are learning. Now, instead of doing one projection, if you do multiple of this projection, the idea is you will learn better features. So, that is why generally you do not use one hidden layer, you use multiple of these hidden layers, and that is what a feed forward neural network or a multi-layer perceptron it is also MLP, but with a single hidden layer. So, coming back, so in practice we use more than one hidden layer, okay, because otherwise the number of neurons in that one hidden layer needs, I mean, it might be a very big number. So, to avoid that, we use reasonable number, but multiple times, okay. Okay, so now let me draw then again the same thing, but with more than one hidden layer. So, maybe two hidden layer. So, we have our x1, x2, xk, h. Now, I have to use different notation. So, h11, h12, h1p. You can see that I changed the notation because now there will be multiple of this h, at least two of this h. h21, h22, h2q. Now, you can see that each of these layer can also have different numbers of neurons. It is not necessary that the hidden layers will have same number of neurons. And then you can have multiple y as well, but I am going to draw only one, but you can have multiple of this y. Okay. And now, let us complete the diagram. Okay. So, basically you connect all the possible nodes. Okay. Okay. So, let me now also write the nomenclature in a more formal manner. So, whatever circle you are seeing, that is my node. Also you can call it your neuron. Okay. Whatever arrows you are seeing, that represents my edge. Okay. And then as I said, each edge has a weight. Okay. And then each node has a bias, but this is except the input nodes, except the input nodes. Input nodes means x1, x2, xk.
Sir, universal approximation theorem, you said single hidden layer can approximate any continuous.
Correct, can represent.
This is theoretically, we can say it is proved.
Correct.
But in experimentally, if we increase the number of sides of the hidden layer, does it observe that it improves the result?
No. The reason is that theoretically you can prove it, but at the end of the day, to find these weights and biases, you have to solve a non-convex optimization problem. So you will get stuck in the local optimum. So it can, but maybe even with local optimum, you have to do a million trials to get the global optimum. If you can get that, then yes, but then that is not practical. Okay. Okay. So the circles are the nodes, neurons, whatever you call it. The arrows are the edges. Each edge has a weight, and each node except the input node has a bias. Okay. So based on this, can you tell me what is the number of parameters of this network? What is the number of parameter? It's a small problem, right? Tell me. Let's go step by step. First layer, up to first layer, I mean first hidden layer, how many? Pk plus P. Pk plus P, right? Let's write it down. So first you said correctly, Pk plus P. Then second to I mean first hidden layer to second hidden layer, Qp plus 1 times Q. Maybe I should write capital Q, right? I mean I am using capital here. So plus Qp plus Q, and then Q plus 1. Right? So you can easily calculate the number of parameters. If I make it even more complex, 10 such layers and all of those things, it's easy to calculate what is the number of parameters. But it's difficult to work with the number of parameters because this number will become very large, as you can imagine. I mean, imagine P to be 1000, Q to be 1000, and then you see what is the number of parameters, maybe K to be 100. So you have 100 features, 1000, 1000, and then 1. So it will be 100 times 1000 plus 1000 plus 1000 square plus 1000 plus 1001. So you can imagine that is going to be a large number. But again, what is large? I mean, those working on deep learning will say this is a small number, what I just said, because the large models have trillion parameters. I mean 2.5 trillion, 1.8 trillion, these are the numbers we are talking about when we call large language model, for example. So large, small is always a relative number. Large compared to what? It is large compared to a linear regression. It is small compared to a large language model. So these are again relative, but the number is quite high. I mean minimum you are looking at probably 100,000, if not more. So that's what you are looking at. Okay. Also it is large from an optimization point of view. When you look into the optimization literature, the number of design variables is generally in a range of what? 100 is a high dimensional problem. We are talking about not 100, 100,000 minimum. So from an optimization point of view, this becomes a high dimensional problem. Okay, so it depends what context you are looking into it, whether it is high dimensional or low dimensional. It depends on the context of the problem and what you are comparing with. Right? Any question? let me complete this part then. So now there are some terminologies, some I have already told, some I have not told. So let me bring this here and discuss it now. So as I said, this is my input layer. These two are my hidden layers, and this is my output layer. This is how it will always look like. I mean you will have input layer, hidden layer, output layer. These three things you will always have in a neural network, right? Now there are two things that I want to talk about. One is this direction. Okay, this direction is known as the width of the layer. The width of the first layer is k, the width of the second layer is p, the width of the third layer is q. So this direction, the number of nodes in a layer, is called the width of the layer. Okay, and now the other one, this direction is called the depth. Okay, this direction is called the depth of the network. So number of hidden layer increasing means the depth of the network is increasing. Number of nodes in a layer increasing means the width of the network is increasing, or width of that layer is increasing. Clear what is width, what is depth? And from this depth the term deep neural network comes into picture. So deep neural network is a network that has at least two hidden layers. So if it has a single hidden layer, we call it a shallow neural network. So universal approximation theorem is for shallow neural network. A deep neural network is a neural network that has at least two hidden layers. So that's how the name deep neural network comes into picture, and that's how the term deep learning comes into picture. The course is about deep learning. So the term deep relates to depth, and it will at least have two. If it is less than two, then it's shallow. Okay. So a deep neural network is a neural network with at least two hidden layers. Not two layers, two hidden layers. That's a distinction you should make. If it has two layers, that is input and output, that is any model. Any supervised learning model has an input and output. So two hidden layers, not two layers. Okay. So the clear how the name deep comes from the term depth, and depth is the number of layers, number of hidden layers. Okay. And parallelly, we should also be aware of what does width means. Width means number of neurons in a layer. That is the width of that layer. Okay. So now let me do one more thing. Let me write the mathematical expression of how you will compute y as a function of x for this network using the vector notation, and from there let us see if we can conclude something. Okay. So mathematical representation. So we are going to give some names. So the first layer we are going to call x, which is a vector. Second layer we will call h1, and it's a vector again, p dimensional. Third layer we will call h2, it's again a vector, q dimensional, and the last one is y. Okay. So you tell me vector notation, keep that in mind. h1, how will I write it? We did it a little while ago, so you should be able to tell. Sigma 1, then w1 x plus b1. x is my vector, b1 is my vector, w1 is my matrix. What is my h2? Sigma 2 w2 h1 plus b2, right? What is my y? I am going to write sigma 3, but you know that for regression that might be linear, for classification it might change, but in a generic sense I will write sigma 3. Okay. So, what is y? Sigma 3 w3 times h2 plus b3. Now, in a generic sense you will have, I mean I have written y as a vector. Keep in mind that in my diagram y is a, or in our diagram y is a scalar. So, I am generalizing, so that is why I have written y as a vector. So, this y can be a vector as well, and if y is a vector, this b3 should also be a vector, otherwise this b3 should be a scalar. I mean b3 and y3, y should be of same dimension, as simple as that.
Sir, H2 is
Sorry, correct. Thank you. Okay. Okay. So, now combining these three equations, can you tell me how should I write y as a function of x? I want to write y as a function of x, not through h and all of those things. This h I want to eliminate, which is very simple. We will just substitute them. So, let us see. So, from here we can get y is equal to sigma 3 w3, and then I have my h2. So, it will be sigma 2 w2, and then sigma 1 w1 x plus b1 plus b2 1, 2, 3. Okay. So, I think one more bracket, right? Check the bracket, okay, the closing of the bracket. I think it is probably correct. Okay, but yeah, check that whether I have closed the bracket correctly or not. It might be a little bit here and there. This is how it will look, right? What can I conclude from here? Each of these three expression h1, h2, h3. Do you agree with me that each of these expression is a function? I mean the right hand side is a function. Sigma 1 w1 x plus b1 is a function. Sigma 2 w2 h1 plus b2 is a function, and the third one is also a function. So, if all of these three are function, what is this expression doing? It is composing the functions together. So, a neural network is nothing but a composition of function. So, when you think about neural network, I know mostly this diagram will come to your mind, but one more thing should come to your mind, that it is nothing but a composition of functions. Okay. So, neural network is nothing but a composition of functions. Okay, before I forget, today there is no practical. Practical starts next week. Okay, so next Monday the practical starts, because yeah, there is yet nothing I have covered that can go into a practical. Okay, it was mostly review and neural network we started on Friday, so there is not enough time. Okay. So next Monday onwards there will be practical. So practical seats will be communicated beforehand, but today there is no practical. Okay. If you are wondering what is the location, I don't know. I will have to book and then let you know. Okay. So a neural network is nothing but a composition of function. And in many articles, many journal papers, you will see that it will, this expression that I wrote earlier will be written in this form. Sigma 3 W3 sigma 2 W2 sigma 1 W1 x. Okay. You will see that the B term is missing because so you can assume that it is being absorbed inside W. But this is a representation you will see in many journal papers that you have to read, let us say very soon as the project starts. So if you see this notice this kind of representation, this is nothing but that representation. This circle that you are seeing, that means composition operator. This circle means, you see many circles, right? 1, 2, 3, 4, 5 circles at least. So the circle means composition operation. Okay. So this is a composition operation, and neural network is a composition of functions, so you can understand why it is like this. All of these are. Yes, it basically represents this thing getting multiplied, that is all. Okay. This expression is what you will do practically, but you can understand that this is quite long. So what you do is, whenever something is long, we come up with some compressed representation. This is one such representation of it. Okay. Any question?
Can we absorb W?
W you cannot absorb. I mean, those are learnable, right? So what will you learn then?
So the bias is also.
No, x you can always write x as 1 comma x, 1 and then x, and then that can go in. So in that sense, I say you can absorb. When I say absorb, it means that it's not that it is not there. It is there. I am not writing it. That's what absorb means here. So in this case, what was the original dimension of x? K, right? In this case, it will be k plus 1. You understand what is happening? So that means that plus 1 will become a 1, and that will get multiplied with W1. So W1 will have that bias term. So same thing. So it's by absorbing, I don't mean that I have to remove it. Okay. Okay. So a neural network is nothing but a composition of functions. Okay. But to use the neural network, you need to know or learn the parameters. That is true for any machine learning algorithm. You need to know what is W3, W2, W1, B1, B2, B3. These are not known to you a priori. This you want to find out. You want to train your model by solving some optimization problem, right? So, and that you need to find out. So, these W's and B's are the parameters of the neural network. What are the hyperparameters of a neural network? Number of hidden layer, number of nodes in a hidden layer, input and output you cannot touch. So, only the nodes in a hidden layer, the activation function you select, and obviously the optimizers, other hyperparameters will also come into picture. So, theta is equal to all the weights comma biases combined together is the or R, okay, is the parameter of a neural network. And parameter means it is to be trained. The loss function you will try to minimize, and by changing the parameter. Okay. And then parallelly, as I said, number of hidden layer with, I am intentionally using this term, which is number of neuron of each hidden layer, activation function, mostly activation function of all but the last layer. As I said, last layer activation function is often determined based on the problem you are solving, but the other layer activation function is kind of heuristic. So, activation function, sorry, these are my hyperparameters. By the way, practically or theoretically speaking, grammatically correct, hyperparameter actually means parameter of parameter. Actually, hyperparameter means parameters that define the parameter, but that is not the definition we use in deep learning. In deep learning, hyperparameter means those are also parameters that you tune and do not train. Okay. In some sense, parameter of parameter is true actually, but not in all sense, and I'll tell you why. Number of hidden layer, right, will dictate the size of theta. Weights will increase. So you can imagine that this is dictating the number of parameters you will have. Width of each hidden layer will also dictate the number of biases and the number of weights. So these two can be thought of as parameter of parameter, but you cannot think of it like that for activation function. I mean, activation function do influence what weight you are learning, but you cannot think of it like that. So in deep learning, in this course, hyperparameter means parameters that we do not train the network for, parameters that we tune by using, let's say, validation data or by doing a grid search or something like that. So that is the definition for this course. If I teach probabilistic machine learning when I teach probabilistic machine learning, then I go by the definition parameter of parameter. Okay, so keep that in mind, this distinction in mind. Okay, so how to train the network then? How to train? Remember, we talked about training in the last lecture, I guess, if I'm not wrong, or the last lecture, I forgot, but we did talk about training, not neural network, but we talked about two approaches for training. What were the two approaches? Direct and indirect approach. What was the direct approach? You take the gradient, compute the gradient, equate it to 0 and solve the equation. For neural network, direct approach is not an option. Even if you take the gradient, equate it to 0, you will get a highly nonlinear equation which is to be solved iteratively. So direct approach is not an option when it comes to neural network or deep neural network. Okay. So in deep learning, direct approach is not applicable, which means the only option we have is indirect approach. Indirect approach. Remind me, what was the indirect approach? Gradient descent. Gradient descent was my indirect approach. And what was the formula for gradient descent? Theta t plus 1 is equal to theta t minus the step size or learning rate eta multiplied by gradient of the loss with respect to the parameter. So indirect approach is theta t plus 1 is equal to theta t minus learning rate theta t. Okay, this is my gradient descent. And I told earlier also, what do I need to use gradient descent? There are two things. One is my learning rate eta, I need it to update. The other is my gradient of loss function. Actually, loss function I don't need. I only need a gradient of loss function. But obviously, how will I calculate gradient of loss function without knowing the loss function? So I need loss function. Okay. So Eta is another hyperparameter. You don't train for eta, you kind of fix eta based on heuristic. Okay. So this is another hyperparameter. Okay. And this is what we need to compute. Needs to be computed. Okay. And how to optimally compute it is a major portion of deep learning. Let me put it that way. To actually use deep learning, I mean, think about it. Now, neural networks were developed in 1970s, something like that. But they were not being, people were not able to use those. The reason was that how to train and find the weights and biases. Then what happened was that the backpropagation algorithm was proposed, which allows the user to find these gradients efficiently. Obviously, later automatic differentiation came into picture, which makes life even simpler. But automatic differentiation is nothing but an implementation of backpropagation. Backpropagation is the algorithm. Okay, so this gradient needs to be computed, and that's what we will talk about next, which is backpropagation. But we will come back to backpropagation again and again. For example, when you go later and talk about CNN, we will come back to backpropagation in CNN. When we go ahead and talk about sequence modeling and we talk about RNN, we will come back how to do backpropagation for sequence modeling, which will be backpropagation through time, BPTT. So, and similarly, we will keep on coming back to this computing the gradient part, right? This computing the gradient is central to how modern deep learning algorithms are trained. So, this is very important. Okay. So, computing grad of theta L theta. This is central to training a deep learning model, right? This is a central piece. So, now to discuss this, what we will do is as follow. We will not directly try to compute the gradient of, let us say, a deep neural network. We will take a single neuron, define a loss for that, and try to see how the gradient is computed, and if we can formalize it. And from there, we will see if we can extend it and come up with an algorithm which will do this for us. So, that will be the steps that we will follow. First, we will do it for a single neuron. From there, we will try to identify patterns. Using the pattern, we will try to come up with an algorithm, and that will be the backpropagation algorithm basically, right? Okay. So, probably will not complete it today. 20 minutes is not enough for this, but let us start, right? Whatever we can do, we will repeat some portion and complete it on Thursday. So, let us consider a single neuron with least square loss function, least squared loss. Okay, we are considering a single neuron with a least square loss. So, what is y in that case? Y is equal to sigma W x. I am not writing transpose, basically I am already writing it in rotated form. W x plus b. This is my neuron. And what is my loss? Loss is, I can write a half, but I am not writing it. So, let us say t minus y square. Single, right? So, t minus y. T, what is t here? Target, the label. Y is the prediction. mean squared, so there is a square. And then a single neuron, so y is equal to sigma wx plus b, not a composition of function. Okay. I want to calculate with your help gradient of L with respect to W and gradient of L with respect to B. Okay. So, you will tell me what to do. I mean, you obviously know this, but tell me step by step and we will follow. So, gradient, so what is it equal to? First, you will do the derivative of L with respect to y. What will that give you? Del L del y. Then you will do derivative of y with respect to W. And this is equal to, let us go. So, del L by del y is minus 2 t minus y, right? Minus 2 t minus y. Del y by del w is equal to, I can divide it if the inside term is z, so I can write del y by del z by del w. I mean, if I consider this as my z, so then this is equal to del y by del z by del w. This is equal to minus 2 t minus y. What is del y by del z? Sigma dash. I mean, I have not defined a sigma. I mean, sigma can be ReLU, can be sigmoid. So, because I have not defined it exactly, we can write sigma dash, right, which is the derivative of the sigma. So, sigma dash z, which is wx plus b, multiplied by del z by del w, which is x. Okay. Now, I want you to also help me compute the gradient with respect to b, because we want to observe what is happening when we are. So, that is why we will do both manually. So, let us do the b one. I will write it here. So, gradient, this is equal to del L del y del y del z del b, right. Now, del L del y is minus 2 t minus y, this second one is sigma prime wx plus b times del z by del b is 1. Actually, I should write one more sentence here. So, this is equal to minus 2 t minus sigma wx plus b sigma prime wx plus b x, right. I mean, if I am being complete, that is that statement, there should not be any y. Similarly, this is equal to, again the same thing, minus 2 t minus sigma wx plus b sigma dash wx plus b. Okay. Clear? Now, the important thing, what do you observe in these two calculations? There are two observations. Can you tell me what are the two, what are you are observing? Maybe there are more, I do not know. I can observe two things, but what do you observe from the calculations we did just now?
Gradient with respect to weight is gradient with respect to bias time sense.
Okay. Anything else?
Gradients got reused.
There are many of the gradients we are reusing it. So, if I am doing it manually, I am actually doing the calculations again and again, right. Absolutely. And this is what motivates backpropagation. There is one more observation, which is non-trivial to observe, that this was a single neuron and this is the calculation we did. Imagine a p equal to 1000, q equal to 1000 and do it by hand. I mean, not possible. So, this is cumbersome not scalable if you try to do it by hand. That is the first observation. And the second observation is if you write a code and try to do it like this, then many of the calculations are getting repeated, which is wastage of computational resources. These are the two major observations that led to the development of backpropagation. So, observations. The number one is calculation is cumbersome, and the second one is calculations are getting repeated. Okay, these are the two obvious kind of observations from here. And now you can also observe a pattern like was pointed out, that gradient of weight is equal to gradient of bias multiplied by x, but will that generalize to, let us say, CNN and all those things? Maybe not, maybe yes. So, we are not using that observation right now, but anyways, if we can formalize it and give it a structure, maybe that observation is what we are using, but not explicitly but implicitly. Okay. And in fact, that is what we will do. Okay. So, hand calculation is not an option, and things are getting repeated when we observe these things, right. So, how can we reduce this? So, backpropagation allows us to formalize gradient computation. Okay, backpropagation BP allows us to formalize. So, let us see how we can formalize. Okay, nothing difficult, we will just break it into steps, that is all we will do. So, going back, now in backpropagation, what we will do is as follow. There are two calculations we are talking about. One is given x calculating L, right. Given x you want to calculate y and hence calculate L. If I go back here, the left hand one, right, given x you want to calculate y and hence calculate L. This we call as forward pass, because this is going from left to right, this is following the, if I go to neural network, this is following the arrow direction. So, direction of the arrow is being followed, so forward. So, this we call as forward pass. And when we are computing gradient, you see we are starting from L and going in the reverse direction. So, that is why it is called backward pass. And because of this backward pass, the name backpropagation came into picture, backward back. So, that is where this name backpropagation comes into picture. So, forward pass. Okay. So, what do we have? We have x, w and b, right. So, we can write, let us say x prime is equal to wx, or maybe I do not write like prime. Let us write z1 is equal to wx, z is equal to z1 plus b, y is equal to sigma of z. This y can be further decomposed if I take a particular, let us say, activation function. For example, if I take sigmoid, I will first calculate x, I will make it z2 is equal to minus z, z3 is equal to exponential of z, z2, and then z4 is equal to 1 plus z3, and then 1 by, and I can break it into more number of steps, and I will show it to you, not today, but sometime later, and that is what automatic differentiation does. But for now, you can imagine that all I am doing is that instead of doing the calculation together, I am breaking it into steps. And then the last step is y, so maybe z2 is equal to t minus y, and then L is equal to these are the steps we are doing, right? These are the calculations. You see, this is exactly equal to what? Sigma Wx plus b. So, T minus sigma Wx plus b whole square, right? Clear? Backward pass. Backward pass. Backward pass will be, we'll start with del L by del Z, right. So, del L by del Z2, this is equal to 2 then del Z2 by del Y, this is equal to minus T minus Y. Is it correct? No, 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 minus 1, minus 1. Minus 1. Then I have what? Del Y, del Z, sigma dash of Z. Then I have del Z, del Z1, which is equal to 1, del Z. These two will happen in the same step. So, I am writing side by side is equal to 1, and lastly del Z1 del W, which is equal to x, right. So, you calculate these derivatives in steps, and now you can follow the path because chain rule, multiply them, everything gets calculated only once, just do the product and that will give you the gradient, right. So, from here just product, obviously following some path, not random product will not give you anything, following proper path to obtain the gradient. Okay. This can be better understood if I draw what is known as the computation graph. So, there is this idea of computation graph where you show through an arrow how this computation is happening, the left hand side, and that actually gives you the notion of parent and child, and that allows you to compute this gradient and find the path. Okay. And this is the last thing for today, the computation graph. I will stop with this. So, computation graph. Okay. So, you have to start with, see what you have, W and X. Always look at the right hand side. Okay. W and X. So, you have X, you have W. These two things gets combined, and what do you get? Z1. Then along with Z1, what do you have? B. You combine them, you get Z. Now, on Z you apply this sigmoid activation, so you get sigma Z, which is Y. So, from here it is a single path to Y. From Y you go to Z2. So, for that you need a T. Z2, and from here you go to L, right. This is the path, this is what I had written earlier. I mean, you see them together, you will understand. this is the forward path, or the, I mean the computation forward pass rather also. So if you go left to right, that is the forward pass. If you go right to left, that becomes the backward pass. And for example, x and w for example are the parent of z1, because when the arrow is connected, the arrow head points towards the child, and so the arrow head points from the parent to the child. The arrow head points from the parent towards the child. So if I ask you what is parent of z1, the answer is x and w. What is parent of z? Correct. What is parent of L? What is parent of Z2? Correct. Clear? So this is the notion of parent and child. We will need it for writing the backpropagation algorithm. Yes. So what I was saying is that this is the forward pass. And this will be my backward pass. And now you can see that if I have to reach B, right, how will I go? I will follow the arrow in the reverse direction. So from L, I will go to its parent, which is Z2. From Z2, I can go to T or Y, but I will go to the parent, which will take me to B. So I will go to Z. From Z, I will go to B. So I will follow the parent-child kind of graph in the reverse direction. From child, I will go to the parent. Okay. So while backpropagation or while computing the gradient, we go from child to parent. While forward pass, we go from parent to child. Right? So I will stop here. I have 3 minutes, but I don't think I will be able to complete it. Maybe I'll do one more thing. Wait, let me use this 3 minutes also. Okay. Now this was easy, obviously, and this was a univariate chain rule, right? Univariate backpropagation or univariate way. Let me just show you the multivariate case, and then we'll stop. Okay, I'll use this 3 minutes. So let's extend it to multivariate. And for multivariate, let's say I have a function f, which is function of x and y, but x itself is function of time and y is also function of time or t. So I have a function like this. Okay. What will be the computation graph for this? Can you tell me? Tell me the computation graph for this. So what is the absolute parent? Absolute parent is a term I am coining, but absolute parent means a parent that don't have any parent, right? T, right? Right? T. So that is also known as the root node, by the way. I mean, the root node is a formal term. So T, right? From T, what will you calculate? X and Y. And from X and Y, you will calculate F. Okay. This computation graph is okay. Now you see that now what will happen was not happening earlier. So I want you to calculate the total derivative of f with respect to t. Total derivative. What is the total derivative? How do you calculate it? You go from f to t following all possible paths. Right? So how many paths are there? 2 paths. So the total derivative will be then del f del x dx dt plus del f del y dy dt. Okay. This is actually what is needed for neural network, not the univariate one, because we will have multiple nodes. This is what we will need, and we will build on this in our next lecture. I mean, this is just I wanted to just start it. So we'll start probably from we'll recap this part, the computation graph, and then we'll start from this multivariate case, and then we'll complete the backpropagation in our next lecture. Okay. Thank you.